Now, much has been said of the supposed equivalence between entropy and disorder. Entropy, a quantity that initially arose in the context of reversibility in a thermodynamic heat engine, and disorder, a difficult notion to pin down, but typically equated to fairly ambiguous concepts like chaos, like randomness. Now, such an equivalence is perhaps understandable, given that for very simple systems, it is true that low entropy states correspond to more organisation than their high entropy counterparts. But in all honesty, this analogy very quickly breaks down for many examples. And entropy as a quantity generally is actually very difficult to define for systems that are not in equilibrium, that are open, that are non-linear, all of which apply to the behaviour of living organisms. And that's what I care about. I care about life, and of using this framework of entropy and engines, inference engines, heat engines, to understand the fundamental underpinnings, a fundamental action of living things across all different scales and sizes, from molecular biology to neurobiology to geobiology. And this problem of definition, the solution of this problem, how do you define entropy for systems that aren't in equilibrium, that aren't closed, comes from the world of Bayesian probability, where entropy has a completely different interpretation. It's understood as a measure of the further information required to achieve full certainty. It represents a state of knowledge of a system and is intrinsically related to the observations an agent has on its environment. The idea is that you have an agent that has access to observations, measurements, knowledge, expectation values, and it uses these to inform a model, a probability distribution, a probabilistic description that has a corresponding value for entropy that represents a degree of certainty, and we'll get into a bit more of that. And it's this ability of entropy to be defined by a model that allows it to be applied to a wider variety of physical problems. But before we get into that, let me give you an example, something to hold, so you can understand exactly what I mean and understand more of the true nature of entropy. Let's say I got two different boxes, and in one of the boxes I put helium and the other I put argon. Now, helium and argon are pretty similar. They're both noble gases, so they're full electron shells, they're monatomic, but there is one big difference, which is that argon has a lot more nucleons in its nucleus than helium, so it's a lot slower and heavier. And what we're going to do is we're going to warm them up. So we're going to start them off at 0 Kelvin, absolute zero, and we're going to warm them to room temperature, about 298 Kelvin. So the question is, once I've warmed these boxes up, which of these has a higher entropy? I suppose if you subscribe to this notion of entropy disorder equivalence, you might be inclined to rephrase the question as, which of these boxes has more disorder? You might have trouble assigning orderliness there. I mean, how do you decide? They're basically just balls bouncing off the walls of a box. I guess if I was pushed, I might say that it was the helium box. I mean, it seems more disorderly to me for balls to be messily ricocheting off the walls more frequently. I mean, I don't know. Than in the argon case, where they're a bit slower and easier to keep track of. I mean, that's the problem with using a quantity that doesn't have a definition, is that it's just in the eyes of the beholder, right? But if we go out and perform experiments, we find that it's the argon box that has a higher entropy. And this isn't some mystery. This is easily understood from the context of both Bayesian probability and molecular and classical thermodynamics. All right, thermodynamics. Let's talk about that. So thermodynamics is about energy, the way that energy is distributed within a system or exchanged between a system and its environment. And the trick to understanding this example is to look at the way that energy is distributed inside these boxes, because each individual atom isn't moving at the same speed. It doesn't have the same kinetic energy. Actually, let me just show you what these distributions look like. So in this argon case, you can see the distribution is broader. And that's significant because it means that the spacing between energy levels is smaller, so there is a larger number of ways of distributing a given amount of thermal energy amongst the collection of atoms inside the argon box. And in the helium case, therefore the entropy is higher. Now you might be thinking, well, that's what I mean by disorder. It's a way of analysing a total number of microstates associated with a macrostate. If you have two different systems, one of them has a larger number of ways of arranging the energy than the other one, then obviously the entropy is going to be higher. Fair enough. The problem is that, again, we're still in this context of closed equilibrium systems. Once we start moving away from that, these microstates have to be substituted for something more like trajectories. The allocation of orderliness becomes even more ambiguous. And I would also argue that even in this equilibrium framework, typically I've seen a tendency for disorder to be equated more to something like position, location of particles, way of arranging the physical location of particles than configuring energy inside of them. So the emphasis needs to be on the way that energy is distributed. Now, from a Bayesian probability perspective, there's also a perfectly equivalent explanation. So recall that we started from this state of 0 Kelvin, which is a significant state because at 0 Kelvin, the atoms inside the boxes aren't moving. We know with full certainty what their energies are. They're basically zero. And as we warm the boxes up, we move from that state of full certainty to one of some degree of uncertainty. And entropy in Bayesian probability is related to a measure of the further information required to achieve full certainty. So it's going to give us a sense of the amount of knowledge we've gained or lost. And so as we warm the boxes up, because the distribution of helium is sharper, we're relatively speaking, relative to argon, we are more certain about any one individual atom's state. And therefore the entropy change associated with the helium box is less. Does that make sense? So you see that entropy is this quantity we can think about in a couple of different ways, right? Like as a measure of the spread of energy or as a measure of uncertainty in terms of probabilities. And that's what makes it intriguing, at least, regarding living things, because of the most amazing ways that life moves energy around and also typically makes very, very good inferences as well. Now, there's probably another thing you've heard of about entropy, right? Like that it's always increasing, the second law of thermodynamics. This is a little bit misleading, I think, because honestly, any system is going to have constraints that serve to ultimately limit that increase. So the second law is actually about the tendency of systems to reach states of maximum entropy. And in probability as well, there's a principle of maximum entropy, but it sounds pretty different on the surface of it. It provides a means of generating a best guess probability distribution. This goes back to that thing I was talking about earlier as a broader way of thinking about information and the conversion of presumptions into predictions. And it has the tendency to reduce quite well to examples in equilibrium mechanics, like our boxes, for instance. If we're the agents in this case, we can ask, what fundamental information do we have about the gas inside? Well, in terms of the position, we know that the atoms are somewhere inside the box, which doesn't sound like much, but actually does provide us with a constraint. In terms of the momentum or the kinetic energy, we can make a very safe assumption and suppose that energy is spread evenly among all its various forms. And that serves to provide us with another constraint. And with those constraints in hand, and alongside some quantum mechanics, which I'll go into in the notes, we can use this principle of maximum entropy from probability to convert those assumptions into probability distributions like I showed you earlier, and an expression for the entropy of the box of gas itself. This is the Sackur-Tetrode equation. It's a beautiful equation with a very rich history. And within it, crucially, is that dependence on mass, something that arose from our momentum consideration that gives rise to the discrepancies in entropy we see between helium and argon. And it's such an amazing equation because it doesn't seem obvious that you could go from making a very basic set of reasonable assumptions on what is fundamentally known about a box of gas at a particular temperature and end up deriving an expression for a quantity that you can actually measure in an experiment using an instrument that's only detecting the heat given off as an element warms. And so in this nice and simple equilibrium case, the second law of thermodynamics and the maximum entropy principle of probability are more or less one and the same. But it is fair to say that once you start moving away from equilibrium, it gets much harder to see how to keep these two different interpretations of entropy, these two conceptions of the second law, consistent with one another. Fuck me, that's beautiful. Look at this. Wow, look at this. All the way around. I'll just quickly explain what non-equilibrium basically means. I mean, if you imagine some imbalance between opposing forcings or different processes within the system. So, for instance, for our box, if we were to rapidly and randomly warm and cool the box by varying amounts, you can imagine there's just no constant momentum distribution to be found. I mean, not only is it constantly changing in time, but say it doesn't have any correlation with its past behavior either. So even talking about the entropy of the gas is no longer meaningful, as it isn't obvious how to define it in the first place. And usually when we're thinking about non-equilibrium systems, we're not interested in boxes of gas. The reality is that they pop up in nature absolutely everywhere, wherever there's turbulence or dissipation, basically. So that may be matter accreting onto a star or a black hole, or the evolution of planetary atmospheres, or the climate in our own atmosphere, or the carbon cycle as a whole in general. Carbon is an atom. It manifests in many different forms on the surface of the Earth, and it's constantly shifting between those different forms. So, for example, carbon dioxide in the atmosphere can be absorbed by the oceans. It can be re-emitted back into the air by the oceans. It can be converted into glucose via photosynthesis in plants. It can be dissolved in raindrops and I think eventually become rock, or at least go out to sea. So if this system was in equilibrium, then all these individual transport processes would still be occurring, but they would be cancelling each other out, such that the overall amount of carbon in each of the individual reservoirs themselves would remain the same. And for 10,000 years, that was the case. Our planet was in a remarkable state of equilibrium until we continue to decide to make widespread use of fossil fuels, kicking this system well out of equilibrium and resulting in changes to our planet that will now inevitably be lasting for millennia at least. And this concept of there being a cycle of processes that are effectively biased in a particular direction is a hallmark of those that are enacted by living organisms. And it's what gives them access to means of energy extraction that would otherwise be forbidden in equilibrium. So there are way more ways for systems to be in non-equilibrium than to be in equilibrium. But there are some ways for systems to be in non-equilibrium that allow for us to discuss and construct similar stationary principles that resemble those that govern conventional equilibrium thermodynamics. So we can look at systems in steady states or homeostasis. We can look at concepts like entropy production being minimized across a boundary or maximized that let us extend our discussion on thermodynamics a little bit beyond that 20th century framework. But I think the main message generally though here is that when it comes to thinking about entropy as a measure of disorder, I just would be very wary of thinking about it in that way. I think that in certain contexts maybe it's all right, but when you start to try and characterize non-equilibrium systems, I think that it totally falls apart. And there are better perspectives to start thinking about entropy in terms of, if you're going to start looking at those kinds of non-equilibrium systems, which are where all the most interesting questions revolving entropy are, regarding life and active inference and time directionality and quantum gravity and everything. So yeah, there you go. Shout out to the 77 people who are subscribed. You guys are literally the best people in the whole world. Thank you. I know this video is a little bit different to that Extinction and Rebellion one that I did, but I think that it's fine. I'm just going to put random things on here, basically. Actually, if you haven't seen the Extinction and Rebellion one, I don't know about the other stuff on this channel, but that video is actually, I think, quite good. And yeah, happy days. Oh, if you want to buy a poster, you can buy a poster. I have a poster. This is my poster. It's fine. I like it a lot. I look up at it and I think that's a nice thing to have in my house. And if you want to have one in your house, you can choose. Not that one. That one's actually not for sale. But there are other ones that you can choose. There's like 100, more than 100. I think there's 200. So if you want to search, then I made a whole museum and you can do that. All right. Thank you very much. Have a nice day, everybody.